Hi everyone! Today I will talk about our recent work on the validation and safety approval of our in-house dual-mode 7 Tesla pTx coil. This work was done as a combined effort of colleagues at the University of Glasgow, the NHS Greater Glasgow and Clyde MRI Physics, and Siemens Healthcare Limited, United Kingdom. Alright, let's get started. I have nothing to declare. At last year's ISMRM, my colleague Shajan Gunamani first presented his dual-mode 8-transmit 32-receive head coil constructed for the clinically approved Siemens Terra 7T scanner. This coil operates as both a parallel transmit or pTx coil and a conventional single transmit coil via a splitter interface. The coil contains an RF shield with eye cutouts for improved patient comfort. As you can see in the figure on the right, it also provides greater coverage than the commercial 7T coil in the inferior regions of the brain, even in single transmit operation mode as shown here. In the latter half of 2019, we began the process of validating the dual mode coil for operation in pTx mode. We were guided by a popular NMR and biomedicine paper by Jens Hoffman et al. And added additional safety tests that were referenced from an ISMRM working group dedicated to the topic. The following steps were performed to validate the coil: bench testing of the coil, full transmit array simulation with the EM software CST, temperature mapping with RF heating, SAR simulations of the coil for various human body models, tractable SAR monitoring via virtual observation points or VOPs, and corroboration of the coil model by comparing experimental and simulated transmit field maps and SAR estimates. The steps in dark blue will be discussed in this poster. We performed temperature mapping in a dedicated sugar-salt agar phantom that had similar electrical properties as human brain tissue. The phantom had 3 oil vials attached at its periphery as a phase reference, as well as a fiber optic temperature probe both internally and externally. Temperature mapping was done with the PRF method referenced here, in which GRE phase images were interleaved before and after an RF heating sequence. The RF heating was applied for 2 pTx configurations, circularly polarized mode or CP, and the CP2+ mode, which is an alternative phase configuration. The acquired temperature maps were compared to the simulated temperature maps for the same input power, although applied instantly. Although there are limitations in the power deposition and heat dissipation in the experimental methods, the temperature maps for both simulation and measurement are in nice agreement spatially and quantitatively. To effectively monitor SAR, the EM simulation of the coil was loaded with 3 human body models that were each positioned at 3 locations within the coil. The 9 total simulations were used to generate 10-gram volume Q matrices. In this figure, we show the 3 body models and their SAR simulations for 1 watt input power with CP excitation. The spatial SAR distribution is not always intuitive as seen by its asymmetry here. VOPs are the standard method for tracking local SAR and pTx in a computationally feasible way, compressing hundreds of thousands of Q matrices into hundreds of VOPs via a clustering method based on the spectral decomposition properties of positive semi-definite matrices. The amount of compression scales with the overestimation factor, which for us was 10%, yielding just 126 VOPs for all 9 combined body models and positions. We validated the VOPs and SAR monitoring of our coil by then comparing the full Q-matrix SAR, the compressed VOP calculated SAR, and the scanner estimates for 3 pTx excitation modes. With compression and safety margins introduced at each step, we verified that the inequality written in bold held true. The final validation of our coil compared the simulated and experimental B1 transmit maps. This was done for the single transmit channels as shown by their magnitude and phase images on the left, as well as the combined CP mode transmit maps shown on the right. The simulated peak B1 was 125 nanotesla per volt compared to 107 nanotesla per volt experimentally for the same input power. After completing all steps of the validation process, the coil was approved by our local safety committee for use in healthy volunteers. To date, we have scanned 9 healthy volunteers where we have collected the in vivo B0 and B1 maps as well as performed static pTx or B1 shimming. This has already shown some improvement in the transmit field homogeneity as highlighted in a few examples here. Our goal is to begin with full pTx scanning very shortly. If you should have further questions regarding the practical aspects of our dual mode coil validation process, please feel free to find me virtually at this ISMRM or hopefully look out for our paper we have just submitted for review. With that, I'd like to conclude by thanking my colleagues who have supported us in our work. Thank you.